Now jump to the slip. What is slip? Okay, so the process by which the plastic deformation is produced by dislocation motion. Keep in mind these things. Dislocation is important thing here. Okay, termed as slip. So the motion of a dislocation, whatever the kind of the dislocation that we have discussed till now, okay, how they move inside the crystal, that is known as slip. Okay, so the crystallographic plane along which the dislocation line transverse in a slip plane. So slip plane and slip direction, they are the two kind of terms that we have to know about that. Okay, and combination of these two things is known as the slip system. Okay, now we are just discussing the slip. Okay, further we will discuss the slip system, but right now for your understanding that you need to know that what is slip. Slip is just a motion of a dislocation inside a crystal system. Okay, obviously, I mean what the kind of the plane that they are traveling through, which is known as the slip plane. Okay, and as indicated in the figure below this, you can see here, this is the figure. Okay, so microscopic plastic deformation simply corresponds to the permanent deformation that results from movement of dislocation or slip in response to an applied shear stress. Okay, so I have discussed that. I mean, what the shear stress means, the applied force basically. The body which resists is internal phenomena that the the upper that body resists that particular force is known as a stress. And if that force is per unit area only, then it is known as a stress. And there are two kind of the stress. Stress is a normal and shear. Shear means if the suppose this is the body, right? Suppose this is your body. Okay, and if you have applied the force like this, irrespective of your types, either it's a compressive or tensile, that doesn't matter. If you have applied perpendicular to your area, then it is known as normal stress. Okay, I mean now you are it's a compressive force. It could be like this as well. Okay, so both are other force applied on the body, but the resistance force that induced inside a material, okay, that per unit area, that area is perpendicular, right? This is known as normal force. But what happen if, suppose in the same figure, okay, if the force applied is if this particular area, and now this kind of the force is applied here, okay, and obviously there would be some kind of here, right? This is known as a shear because along the area you are applying the force. Now the resistive force that induced inside the body per unit area is known as your shear stress. So what is the difference between in this figure? You could have like this. This is your shear stress. So red one is basically the force applied along the area. If along the area, then it is known as the shear stress. And basically there is a the kind of step. If the force applied is along the area, then the resistive force induced inside the body is known as your shear stress. And if the applied force is perpendicular to the area, then this is known as your, and in that case, if the resistive force induced inside the body is known as your normal stress. Okay. So what kind of the force that is going to be come into the picture in this particular thing is a shear stress. Okay. So keep in mind when we talk about the slip, there is a shear stress. I mean the force that is going to be the responsible for that particular movement of that dislocation is a kind of the force which is along the plane or along the area. Okay, so look here in this picture. I mean this is your extra plane or half plane by which you have a dislocations. Okay, otherwise if that particular half plane could not be here, then everything would be perfect of fine, right? It could be like this could be, you know, okay, this could be like here. perfectly matched this way, and this could be like this. Everything would be perfect. But what is the additional thing come here in the picture, which is this particular line. This particular line means this particular half of the edge, right? That has induced inside a crystal. That is basically your dislocation. Or what kind of the dislocation? It's an edge dislocation. So this line or this uh, dislocation is responsible for your imperfection. Okay, and now what is going to the slip? Now you can see here, if you have applied this shear force, or you can say the force by which the shear stress induced inside the material, that will resist, that will pull that particular dislocation towards left to right. Okay, as you can see in the as you can see in the picture B. Okay, what happened? This particular edge dislocation moved to the second one here, right? So it was at the first, now I come to third, sorry, second, now third, and similarly, okay, go so and so, and that at the at the end, they have come out of the plane. Or you can say that if you leave that particular edge dislocation, then you have the perfect crystal here, as you can see here, right? So if movement has occurred, then you can see, I mean, it's a kind of an advantage as well. If there is a dislocation, that is disadvantage things. Okay, but if movement is occurring, okay, and sometimes you do some extra effort to the crystal to dislocate or to give the movement to that particular uh, imperfection, so that you could have the perfect crystal, as you can see here in this particular uh, diagram. What happened? It was at the position A, okay, then came to the position B, okay, then come to C, D, E, and F, and at the end they have come to the at the right, very right side of your crystal. Okay, so by the movement of your dislocation or dislocation imperfection, you could have the you could have the advantage of that. Okay, so sometimes it occurs automatically, and sometimes we do some extra effort, or we provide some energy from externally to dislocate or to give a movement to that particular dislocation. Okay, so this is the way how they move. So this is the plane. Okay, this is the direction of your I mean, if you talk about this particular dislocation or imperfection, this is obviously there would be some kind of the plane there where it exists. Okay, so that is known as the slip plane, and the way in which they are moving in the plane they are moving in that I mean the direction they are moving, this is known as your slip direction. So the motion of the skew dislocation. This was the edge dislocation. Now here is the skew dislocation. So if we talk about the motion of the skew dislocation in response to the applied shear stress, as shown in the figure below, okay, the direction of movement is perpendicular to the stress direction. Obviously, okay, so whatever the direction that you have applied, okay, or the generated force, okay, the direction defines in which direction the movement of particular dislocation will happen. So if we talk about the screw dislocation, okay, so the direction of movement is perpendicular to the stress direction. So whatever the your stress direction is, basically responsible for your movement of your dislocation directions, and that would be of perpendicular. So keep in mind, if your applied force is in any direction, your dislocation movement would be in perpendicular that particular direction in the case of screw dislocation, as shown in the figure here. So for an edge motion, it would be of parallel to the stress, shear stress. So if we talk about the, I mean, here we have discussed above. This is the edge dislocation, right? So if edge dislocation is moving, that would be parallel to your applied force, or you can say the applied shear stress, because that applied force is responsible to induce a shear stress. So in other way, you can say whatever the what direction that you have applied a force, that is responsible for you. dislocation movement, and in case of the edge dislocation you have the parallel. Okay, so direction of the movement of your dislocation is the parallel to the applied force, but in case of the screw that will be the perpendicular. Okay. when metal when metal or plastic deformed means I've already told you. I mean, plastic deformed means when you deform the body, it means you are applying a force over a body that will deformed. If that force is, or that load is only up to the elastic limit, means when you remove the load, the body will regain their shape. Okay, that is known your elastic limit or elastic deformation. But if you cross the sorry, but if you cross the elastic limit, I mean the load that you have applied which is cross the elastic limit, it means you have deformed the body too much, and that deformation will not regain when you remove the load. That is known as your plastic deformation, right? So plastic deformation is permanent deformation. I mean, you cannot regain that. Okay, but elastic deformation means when you remove the load, that then in that case the body will regain their shape by own, which is known as your elastic deformation. But what we are talking about, the plastic deformation, whatever the deformation that we see across the material, that all are of plastic deformation. So some fraction of the deformation energy, approximately of 5%, is retained internally, to the remainder is dissipated as a heat. Okay, so deformations, when deformation occurs, okay, so 5%, approximately 5% is retained internally, remainder is dissipated into the heat. So when you apply the force and the body deformed, the deformations, I mean, obviously what happens, and when you apply the force means that you are investing the energy over the material. Okay, so that energy cannot be, I mean, whatever the first law says us, that energy cannot be created nor be destroyed. What does it mean? It means you can convert the energy. Once you have applied the energy, it means you have just invested the energy. That energy must be stored somewhere else. So what happens whenever apply the force and the body gets plastically deformed, it means the 5% of the body is going to stored inside the body in the form of strain energy. Okay, and rest 95% is going to be dissipated into the environment, which in the form of heat, right? So the major, sometimes it's also as a sound energy, but which is very fraction of that applied force, applied energy. Okay, so the major portion of this stored energy is as a strain energy. As I already told you, the amount of energy that is stored during the plastic deformation is known as your strain energy. Okay, and that is associated with your dislocations. Dislocation means the imperfections. Obvious, the plastic deformation is in self is a kind of dislocations or undesirable things. Okay, so consider the edge dislocation represented in the figure below. There is the presence of the extra half plane of the atoms. As a consequence, there are the regions in which compressive tensile and the shear lattice strains are imposed on a neighboring atoms. Compressive, as you know, that means if you have the pulling force towards both the side on a body, this is a compressive force. And if you have the no, sorry, if you have the pushing force from both the sides, then it's a tensile. And if you have the pulling nature from both the sides on a body, is known as the compressive force. Okay, so shear lattice strains are imposed on a neighboring atom. See here. See, I mean, this is your dislocation. What kind of a dislocation it is? It is your or you can say edge dislocation. So if you have the edge dislocation, you can see here this particular area has been filled with other atoms, of which was basically disturbing your crystalline nature. Okay, so if something has been introduced in a specified area, that means they would be, I mean, all neighboring atom will be in a compression, right? But if we talk about the rest half of that crystal structure below that particular red line, you have not a disturbed element, right? But due to this particular nature, this dislocation, the compressive force has introduced in upper half of that region, right? Due to this, there would be some tension in particular region. Why? Due to this particular atoms. As you can see, I mean, when this particular dislocation come here, okay, they have disturbed all neighboring atoms, and due to disturbance, they have get stretched they have come into the picture like as a compressive force, and that compressive force will disturb also in this region, but that would be in a tension. Okay, they will try to stretch them, but they will, the atom below that red line would try to be in their own position. That's why they are in tension. Okay, so as you can see, where you have a dislocation, that dislocation would be of your compressive nature, and below that you would have a tension, I mean tensile nature. Okay, so it's a very simple to remember that whenever the dislocation appears, or line or edge dislocation appears, it means you are disturbing the neighboring atoms, and that you have occupied the places of others. It means you have repel other atoms. They will try to come their own position. It means they are in compressive nature. Okay, they will try to uh, come close. Okay, but what happens to the rest of that, you know, crystal, or you could say the line which is coming to the bottom of that edge dislocation, that would be in your tensile nature, as you can see here. I mean, above this green portion is in compression, and the yellow one is in tension. Okay, so this was your no. See, the compressive and tensile strain feels for the both lie on the same side. What happens if both the same nature has come on the same side? As you can see, this is the figure. Okay, so if you have a crystal like this, in which compressive force is at the top and tensile force at the bottom, what happen if the same kind of the nature is comes nearer as the compressive at the top and tensile at the bottom? What would happen? I mean, same nature will repel to each other. Same sign will repel to each other. It means the repulsive force will occurs, right? As you can imagine very easily, because this is the compressive and this is tensile, right? So so compressive will repel, and tensile will repel each other. So overall, this kind of imperfection will repel each others. They will not try to come close. Okay. So it means what does it mean? It means they will be having same as it was. I mean, they will increase or enhance your uh, uh, dislocations or imperfections, so that your crystal will not get refined, that will not be a perfect crystal. What happen if the same thing will changed, just opposite to each other? I mean, the compressive at the top and seconds tensile will come at the top. See here in the picture. Yeah, in this picture, green one. So you have the, I mean, one kind of the dislocation is like this: the compressive at the top and tensile at the bottom, and rest other, they have the tensile at the top and compressive at the bottom. It means both have the different nature. At the top you have the one compressive and one tensile. At the bottom you have the one compressive and one tensile. So the different sign will attract to each other. It means there would be some kind of attractive attractive force will occur in this kind of crystal, and due to this you can see, I mean, some edge, I mean, there was where the compressive nature will occur, it means there is a edge dislocation occurs. So half of this line has a edge dislocation, and half of this line has a dislocation, and they have the nature to attract each other. Okay, so attractive force will occur, and due to this both will combine together and make a perfect crystal, as you can see here. I mean, this is the kind of the symbol which denotes, that means the edge dislocation is at the top, and where the edge dislocation is there, that would be in a compressive nature, and half of that part would be in a tensile nature. So this symbol is here, and in second you have that compressive at bottom and tensile at top, and so combined together that will make this kind of symbol, as you can see in in this figure. Okay, so I mean, once such kind of a things, and again same figure, same this figure is suppose here. Okay, but in this case The compressive is at bottom and tensile is at top. It means this just opposite. If you will reverse that image, okay, you will just rotate this particular image through the 180 degree, then you would have the same figure. And if combine them together, it means you would place a one line here as well. That will that will combine together of this particular line. So you would have the perfect crystal. Okay, so here we have shown the same things. So keep in mind, once you have the compressive at top and opposite of that is of other crystals, then they will attract each other. But if the same sense is there, like at the above in the figure A, at the top the C, and we talk about the other crystal, they have also at the C at the top, means they both are in a compressive at the top, they will repel each other. Okay, if the same sense they are, then they will repel each other. But if the opposite sense are there, then it will attract each other, and attract of the opposite nature, that will make up your perfect crystal perfect. Okay, so that is this kind of things is the advantages. This is decidable because we want to make our crystal perfect. So perfection will come out with this particular arrangement. So this is the nature that we are basically trying to get and reach that our crystal. So if this is a symbol of the T, okay, or you can see the H dislocation. So if the opposite of T is there, then it will make you perfect crystal. And in this case, the same symbol will lie. Then this is this T, then plus again this kind of a T, opposite T, that will not make your crystal perfect. So this is not a perfect crystal, right? So keep it in mind.